Yeah, I'm just going to very briefly introduce some application for genetic algorithms, what I did in the past, with the goal of both providing a little bit more detail on practical implementation and on getting comments on how things could be better. It's always easiest to learn from things other people did badly. So I thought I'd provide an example that might or might not be well done. So first, a little bit of context. For a paper, I need to generate a model of a representative neighborhood. And for that means I need to have load profiles for every single building in the neighborhood. And it means I need to have household configuration for every single building. So to specify a household, I need to know how many people are there, how old they are they working, are they commuting, all these things. For privacy reasons, you cannot get these super detailed building level information in any way. But what you can get is mixtures of local, county, and country level statistics. For example, you can get the age pyramid, you can get the number of families, you can get the average family sizes, you can get the number of families with one child. You already see there's overlap between the different statistics, because the number of families and the average family size, number of families with one child, number of families with two children, and the average family size, obviously they overlap. But you cannot deduct from the average family size the number of families with two children, for example. So you have this weird set of constraints that are not independent and that are not always correct, not always matching either, because sometimes one statistic is from 1 year and the other statistic is from the next year, but you need to consider all of them. Additionally, you have a lot of implicit and common sense constraints when you're trying to define a neighborhood. So you, for example, should not have families that only consist of 3-year-old children. You should not define the children as the money earners in the family, and so on and so forth. And additionally, so these are the hard implicit constraints that invalidate the result. Additionally, you have some common sense restraints that mostly need to apply, but are not do not invalidate the results. So couples, for example, should be mostly close in age. If you have 80-year-old and 18-year-old married people, that happens maybe once or twice in the neighborhood. But if every family is looking like that, then something went wrong. Most families should have a father and a mother. There can always be a couple of gay couples or lesbian couples. But if every couple is a lesbian couple or a gay couple, then your neighborhood is not representative anymore either. You should not have too many grandparents with little babies and all these things. So the common sense constraints need to be considered as penalties, but they are not hard constraints, more like soft constraints. And we should consider them as much as possible to make the results better, whatever that means. So Cruz already explained all the basics of the genetic algorithms. So what I did, it didn't seem, so I used the genetic algorithm. Because of the nonlinear overlapping constraints, implicit constraints, and so on, strictly linear mathematical model didn't seem like fun or like a way to actually achieve anything. So I built an object-oriented model for the town, filled it with randomized data, and then for each statistic have each implicit and common sense constraint, I built an evaluation function that output a weighted value, how well the town fits that criteria. Then I built a function to turn the object-oriented model into a bit string, bit array, or genome, and turn it back again, and then use the genetic algorithm to optimize the town configuration. As Cruz mentioned, the mapping algorithm or the data structure in the genome is one of the most important things. What I did is I pre-created the people, because from the age pyramid, I knew exactly how many people of each age and each gender were available. And then I used the algorithm to assign these people to individual households. So I coded every person has 10 bits on the gene. So the first 10 bits, for example, belong to person 1, the next 10 bits belong to person 2, the next 10 bits belong to person 3, and so on. And then by switching the bits and mutating the string and so on, I can change the assignment of people to the different households and then evaluate the entire population, how well it fits the statistics. This might not be the optimal way, but it was one way that was easy to implement. From the class structures in the program, I have a population class that's able to calculate the fitness for a given genome and transform the genome in a population, calls the all the evaluating functions for the population and calculates the combined fitness score. I have the household class, which contains the person. I have the person class, which describes the person and which can identify what household they belong to from the bits. And then I have the evaluators, which take a list of households and then generate a fitness value. As technical parameters, one of the things I found when using genetic algorithms is that there's a lot of parameters you can mess with and that very much influence the results. So here's what I used and what worked okayish. So I have a population of 2,000 people. I limited the number of households to 1,024, which is 2 to the power of 10 or 10 bit. So I end up with a 20,000 bit genome or 2.5 kilobyte. My population size, or the different towns I used in each generation, was 500. I always preserved the top 25%, then generated the children from the top 75%. For mutation, I found a slightly different approach than what Cruz says. Cruz earlier mentioned that he mutates a lot in the beginning and not so much in the end, towards the end. I found another approach, which is to mutate 90% of the children barely, 9% a bit, and 1% basically exposed them to a nuclear accident and randomize, so you don't get stuck in local minima so much. Time per generation was about 0.3 seconds for me. You can see here I did 5,000 generations in, I think, was like half an hour or so. Or no, less, much less. And you can see here there's a rapid improvements for about 500 generations, and progress slows down, but slowly still gets better. Mostly the soft constraints continue to improving. So, for example, one soft constraint was the age difference between married couples, and very slowly, the people in marriage became more close in age. So, conclusion about this is it's provided an easy and quick way to do complex parameterization, which with very messy constraints. I feel my genome transformation function is both critical and has lots of room for improvement. Probably you could do something like you instead optimize the number of families or something, and instead of pre-generating the people, and end up with a much smaller genome, which might be faster. But then your evaluating functions would be a lot slower, probably. Yeah. What I found is extremely useful is that by adding, you can add unlimited number of evaluators and just add them to the fitness function in the end. Because the statistics departments are both creative and frequently contradictory. And what I found is that at least for this problem formulation, scaling seemed to be pretty limited. With 10,000 people already, it didn't yield good results anymore. So frequently, I found you just have to find something that's good enough and then leave it at that. But then the good enough is not sufficient for solving much larger problems. Thank you.